to Calculus 2, section 7.3, Trigonometric integrals. So I hope you spent yesterday reviewing all the trig you possibly could and then dreaming about it all night, whether it was pleasant or nightmares, because today we're going to put all of that to use. I will start by quickly writing those trigonometric pairs for calculus. So we have sine x paired with cosine x. We have secant x paired with tangent x. And we have cosecant x paired with cotangent x. So these pairings are there. And you know that derivative of sine is cosine, derivative of cosine is negative sine, integral of cosine is sine, integral of sine is negative cosine. So you can't escape that pairing. And then you have integral of secant is secant tangent, integral of tangent is secant squared, also derivative of tangent is secant squared, and so on. So you cannot escape the pairing, and if in any of the problems that are going to be in this section and the next section, you run into trigonometric pairing that it's outside of this, outside of these pairs, you will probably have to use basic identities to transform them and then work. So let's say you run into a tangent sine pair. Well, clearly you have to change that tangent into sine over cosine, and then you will have two sines and one cosine, which is sine-cosine pairing. So you have to start this section by reviewing all of the basic derivatives and the basic integrals, and you need to know them all, and then realizing how the pairing works. We are going to do three different types. Oh, technically six, but we're going to talk about sine and cosine integrals, and then secant tangent integrals, and then we'll briefly touch on cosecant cotangent because it's identical, right, to secant tangent, except there are minus signs all over the place. So whatever you learn for secant tangent, you will literally be able to copy and paste into cosecant cotangent and just put some minus signs around. So we'll first discuss sine-cosine pair. Sine x and cosine x integrals. So in order to survive this, we first have to go and visit our toolbox. And the toolbox is that the derivative of sine x is cosine x, and that the derivative of cosine x is negative sine x, and that the integral of cosine x dx is sine x plus c, and integral of sine x dx is negative cosine x plus c. So these are the basic derivatives and integrals that you must know at all times. And then in addition to this, we are going to need sine squared x plus cosine squared x is equal to 1 with the other two iterations where you can sine is 1 minus cosine and cosine is 1 minus sine squared. So that's two other forms. And very important, extremely important, power reducing formulas, which says that sine squared x is equal to, anyone?
Cosine 1 minus cosine 2x
over 2. Very good. And cosine squared x reduces down to? Same thing with a plus. Okay. So technically, if you don't know these formulas that are written here, chances of solving these problems will be slim. And I'm also going to say that we will need U sub. A lot of U sub. So this is all of the stuff that you need to know going into the section. well, into the part of the section, because we are dealing only with sine and cosine now. So we begin with the first problem that you should all solve in 18 seconds. What is the integral of cosine squared x dx? 20 seconds. Oh, time is up like an hour ago. So that will be it. The only way to solve this integral is to use power reducing formula. If you don't know it, there's nothing else you can do. So you must learn. And now we're going to get into a form of, let's do example first. So sine to the 9x times cosine x dx. How would you do this problem? You should know it. U sub. What's u?
Is that x up on the 9 or is that next to the 7?
It's going to be sine x.
Sine to 9 and back down to x.
X, yeah. So what's u?
Sine x.
Sine x. And what's du? Dx. So now I have the cosine x dx right there. And it's time to make this problem that you know from Calculus 1. You are expected to know this problem from Calculus 1. This is a standard 5.5 U sub question. So you should know this from 5.5. What is new today? This one. So this is what's new now. Standard U sub won't work here because when you do the U sub for sine x, you get single cosine x for du, but you have 3 of them, right? So do you have any suggestions of how we might fix this issue? Yes?
Separate the cosine square x and cosine.
Nice. Break down the cosine cubed into cosine squared and a single cosine. Because you want to keep that single cosine for du. And in that case, this almost works because you have your sines on a pile for 9 of those, so there will be u to the 9. You have your cosine x because you broke one cosine off. You have that cosine x dx for du. The only issue is that you have those 2 cosines left. You have cosine squared floating around. And what do we do with that one?
1 minus sine squared.
1 minus sine squared. So we transform all the extra. As a student, I used to attach names to these things. So I said, I just take all the excess garbage, right? That's because I think too fast and I just write. So I say, okay, so now just get rid of the garbage, right? Because that cosine squared was in a way for me to solve the problem. So I would associate that with the garbage, and then I would have to somehow take it out or replace it or something. Those are the associations. That's how my head works. So the trick is to peel off that one cosine and as you can see, you have what you need for u, you have what you need for du. The problem is this cosine squared. Well, you replace the cosine squared by 1 minus sine squared x. And then you will distribute and everything will still work. So integral of sine to the 9x times 1 minus sine squared x times cosine x times dx. When you distribute everything, you will get sine 9x minus sine to 11x, everything in parentheses, times cosine x dx. Use of parentheses is very important here. It's not there for decoration. Both sine to the 9 and sine to 11 need to be multiplied by cosine x dx, each one of those. And now we unleash u sub. Which will immediately transform into u to the 9 minus u to 11, everything du. And from there you should be able to solve it fairly quickly. U to the 10 over 10 minus u to the 12 over 12 plus c, and then the famous sentence, I don't care about u, I care about the x. We bring back x. And that's the solution. What happened?
You can still convert that into sine and cosine both together. Like, take out the sine and x common and then, like, take common derivative.
Yeah, apparently you like pain.
I did that.
So sine to the 9x, cosine to the 4th x dx. Let's discuss this one. What now?
You make use of 2 cosine squared x as a method, the same thing. How to square the cosine squared x?
What happened?
Split sine x?
Split sine x this time. Uh-huh.
Really?
Really?
Eight?
Yeah. You take one of the signs away. Because, and this is where the knowledge of your derivative pairs is going to shine. If u is equal to sine x, then du is equal to cosine x dx. And if u is equal to cosine x, then du is equal to negative sine x dx. Observe that if you peel off one of the cosines, you will end up with the cosine cube. And what are you going to do with that? Scribe. Right? The only thing you can do with cosine cube, scribe. But if you pick out one of the sines and leave that for your du part, you will have 8 sines, which is technically 4 sets of 2, which you can go and do the 1 minus cosine squared. So the trick is to peel off that 1 from whatever is odd. Because you can transform even ones into the other function using Pythagorean identity. So the trick is to just use your eyes, right? Open them and look at the problem, and note which of these exponents is odd. And that's the one you peel off. If both are odd, pick your poison, all right? So if both are odd, pick any to peel off, which will be there for your du part. If one is even, the other one is odd, obviously you will have to pick on the odd one to break off one, and then the remainder would be even, and then you transform those using Pythagorean identity. So now we know how to solve all of the problems which have either of these being odd or both of them being odd.
With all that, you just pick one bit?
Yeah, pick either one. What happens if both are even? I know. In that case, use substitution method doesn't work at all. So I'm not gonna solve this problem here, because what are you gonna do tomorrow, right? I'm just going to write on the side, peel off a sign, and then good luck with the rest. It's gonna be foiling till your eyes pop out. So peel off sine x, and then good luck. So what are we going to do for integral of sine squared x cosine squared x dx?
Rewrite sine x squared x in terms of cosine.
Use 2 powers.
What happened?
1 power. Use formula on each side.
Very good. So, if you have at least one odd exponent, you will peel off from that odd exponent and you will use u sub. If you have only even exponents, you are stuck with power reducing formulas. So, power reduce one, power reduce other one, FOIL, power reduce again, you'll see, and then you will be in a position for U sub. Tonight. Let's go. Well, it's a basic U sub. You can also just treat it as a basic integral. So power reduce this one, power reduce the other one, then FOIL them. Then there will be another term that you will have to power reduce. And then when you expanded all of that stuff, these problems take about a page each. And if you end up working eventually in a tutoring center, or you are currently working in a tutoring center, when the algebra student complains that the problem is too long, just show one of these. I just, because pretty much every problem should be about a page. Welcome to Calc2. Stay a while and listen. What are you laughing at? What are you doing with the number?
I wrote power use. So that's it.
So what do you want to do before? That's how you do it. It's not very fair. Why? Why say it's not 167? No one else in the classroom will take it. I'm talking about records. Power reduce, FOIL, power reduce again. In short, yes. Yes.
I should have left you that.
How do you reduce that again? Because use that and you can yeah. Well, no. So like Cosine.
Yes. Be careful on your second expansion, power reduction, I mean, right? Hopefully you're doubling that angle again. I'll give you another 2 minutes.
It doubles your angle. That's why I call it your angle is the it's 2x. And then so
Would you go after the integral of 4 times the integral of 1 plus, no, of 1 minus cosine squared 2x? I did. Cosine squared 2x. So then, cosine squared 2x is the 1 minus. Wait, could you reduce again after you get the integral of 1 minus cosine squared 2x? Yes, unless I did something.
do that.
Yeah. So I took out 4.
Oh. And still you have that sine for x over
Cosine
x over
like 2x times 1 plus cosine 2x. You FOIL that, you get this.
Yeah.
I'm not sure. Let's see what I'm getting second. Unless I FOIL wrong.
1 over 6 x over
Well, I wasn't sure where to go after this unless I FOIL wrong.
Go line by line. If the foil line in here matches the foil line here, then we'll be that's what the issue. If they are different, then one or both are wrong. And
So
both
now
be
it's
right.
gonna be 1, right?
Yeah.
Times.
So this 1 times 1 is 1. 1 times positive cosine, which is these two cancel, and then you're just left with 1 minus cosine squared of 2x, because cosine of 2x times cosine of 2x is just.
So 1 over 8. Well, that's what I'm saying. So you get 1 minus cosine.
I will follow us also. Like that's immediately what I follow.
How is it over 2? I got cosine 4x over 6.
What's your question again?
I'm just gonna do this because I have nothing else to do.
How do you reduce this?
Okay, let's take a look at this problem together. Or actually, I'm just gonna write it out, and because you know what to do, right? Power reduce, FOIL, power reduce again.
I know what I did.
Oh, so then this. So this.
Yeah, this one's gonna be do this. Keep this one open. This one open. See that this. I'm gonna multiply. So we'll get this one over this one over it's 104. This one 4x. Your outside 4 down here.
Not having dx is -1 per step.
So it's like for this, like
I know you might end up with negative points on this question.
it's gonna be in your I was right. I was right.
So this looks like difference of squares to me. Right? Like x minus 3x plus 3 deal. And now we power reduce again. But now we have 4x. So now what do we have? One minus 1/2 is 1/2 plus cosine of 4x over 2 dx. No, it's a minus because the minus distributes. Great. And now I integrate each one independently. I get 1/4 1/2 x minus 1 over 8. Integral of cosine is positive sign. And we have plus c. And if you want to, you can distribute 1/4. Or you can factor out another half. Maybe that's better. And end up with x minus 1/4 sine 4x plus c. Either way. 100%.
Professor,
Yes.
can you clarify how you went from 1 minus 1 plus cosine 4x over 2 to 1 minus cosine 4x over 2? You divided the 1 by 2?
There's no division anywhere here. You're talking here,
Yeah.
here to here?
No, from there to there.
This 2 makes a half,
Yeah,
and this is also a half, right?
yeah.
So you have a half, 1 minus a half is a half.
Oh, wow.
And
Okay.
then minus this one, right? Minus
Yeah,
cosine over 2.
gotcha.
I couldn't
Okay.
figure out how you got the 1/4 out first.
2 times 2 is a 1/4 out.
The same way you just pulled it out the front.
Yes.
Well, if you got
Why
one,
this is small?
oh, I see, one,
It's the plus. That's what I was saying. It's not just how much you
X and then cosine of 4x sine
6.4.
x
Wow.
4 times 2.
That was an awesome problem. So let's summarize because we are done with sine and cosine. Let's summarize. If any of the exponents are odd, you will peel off either sine or cosine, whatever is odd. Save that for u sub du part. transform everything else to the other function, and use u sub. If you have only one trig function, let's say sine to the fourth, sine to the sixth, or if you have two of them, sine times cosine, but they only have even exponents, in that case you will have to power reduce and keep power reducing until you get into these kind of no exponent sine and cosine functions which you can integrate straightforward. So those are all the tricks that we have for sine and cosine. If any of the or all exponents are odd, just peel one, sine or cosine, whatever is odd, save it for du, and then transform the others and use u sub. And if all powers are even, then power reduce until you can't power reduce anymore. Keep foiling, power reduce, foil, power reduce, foil, power reduce, foil. Sometimes you'll have, I don't know, to do that 3 times. The next part is the spicy part, which is secant tangent pair. And we are going to go to the toolbox immediately. In a toolbox, we have that the derivative of secant x is anyone? Thank you. Which means that the integral of secant x tangent x dx is secant x plus c. What's the derivative of tangent x? Secant squared x, which means that the integral of secant squared x dx is equal to tangent x plus c. Great. We are also going to need Pythagorean identity. You have the sine squared plus cosine squared equal 1. If you divide that equation by cosine squared, you will get tangent squared x plus 1 is equal to secant squared. You can also flip this equation around and write that the tangent squared x is equal to secant squared x minus 1. Sometimes you need that one. So depending on the situation. There are no power reduction formulas that we are going to use for this one. We only have this one and the pairing up there for your u-du situations. So it looks like less work. Definitely less things to remember, right? So let's start with some examples. Tangent cubed secant to the fourth. Now, when I was dealing with this for the first time in Calculus 2 class, I'm always trying to be systematic because I don't like to memorize too many things. So I want to find a pattern, something that will fit everything, right? So as I'm looking at this, and then I look at the problem, I immediately know that, and now I'm really hoping you're looking here, that this is u du, u du. If you pick this to be your u substitution, I don't care how the problem looks like at the moment. If secant is u, this dx will be du. See, this dx goes on the other side because of the x, right? You pick this to be your u, this is your du. So, remember how in sine and cosine you peel single sine, single cosine, and you save them and transform the rest. The reason you're doing that is because those sines and cosines are there for du. Now for du it's much tougher. It's not just sine or cosine, right? Now you have secant tangent that you have to save, or secant squared that you have to save. So looking at the problem here, you can say, well, I have tangent, I have secant. So I can pick any of them to be u. But then the du part actually governs which one is right and which one is wrong. You can't pick both. So you're going to say, if I pick secant as u, then I will need to peel off and save, in a bank, secant tangent. Well, I can peel secant tangent from here, right? And that will leave me with tangent squared and secant cubed. But I'm forcing secant to be this one, which means I have to transform the tangent. I can transform tangent. So that will work. Awesome. But then you say, wait, can I save this? And the answer is yes. So this problem is the easiest problem that you can get because both work. Both of the transformations work. Substitution, sorry. So this is extremely rare. All right? Problems like this are extremely rare. You will usually get that only one of these things work. So you are either peeling off and saving secant tangent for du or secant squared for du. And I'm tempted to do this problem both ways, and I will, because I want to show both approaches, which will not happen for other problems. You will have to do one or the other, whatever is appropriate. So now, let us first peel off secant tangent. So when I take one tangent out, I'm left with tangent squared, secant cubed, and then I have my secant x tangent x dx. And as a student, I used to underline that because that was du. That was set, so I underline it and I say to myself, don't touch it anymore, because you have your du part. Now, as soon as I have that, I immediately know that u must be secant x, and du is secant x tangent x dx. And now you go back and you do the comparison. Secant x tangent x dx, that's this piece, that's du. Secant cubed, there's going to be u cubed, that's checked off. You have extra tangents, right? But that's not an issue, because those tangents can be converted into secants. Like that, right? So now, convert those tangents into secants, distribute secant cubed, and you will have your u sub set up over two integrals, and you will be able to solve this problem. And please, I beg you, next time when someone tells you, what do you know? Show them this. Especially those that say, I've got to get it. Huh? You know, yeah, I read Very unfortunate.
Oh wow, so it just becomes u to the 5 minus u to the 3.
So we are replacing tangent with secant squared minus 1. Distributing. What happened? So now we have u is the secant x. So we have u to the 5 minus u cubed du. The answer 1 over 6 u to the 6 minus 1/4 u to the 4 plus c. And then we go back to the x. Yeah, because that's the, you have to get back to the original variable, right?
Go back to the original.
Yeah. The source. Oh no, I want to do this again. Same problem. Way 2. Integral tangent cubed x secant to the 4x dx. Now this time I want to say that u is tangent x, which means that for du I need to peel off and save secant squared x dx. Which means that tangent cubed x remains, and then I will have 2 secants, one next to the other. And I'm going to underline this, just like I used to do when I was a student, to tell to myself, this is what I need to save for du part. And then since this is going to be my u's, this is garbage, right? So this is the one I have to transform. And secant squared is tangent squared x plus 1. So the integral now becomes tangent times tangent to the 5th x plus tangent cubed x, everything times secant squared x, and then dx. When we use the u sub, that's going to be u to the 5 plus u to the 3 du, which there it is, 1 over 6 u to the 6 plus 1 over 4 u to the 4 plus c. And then you just go back to the original variables, which is x. So it's 1 over 6 tangent to the 6x plus 1 over 4 tangent to the 4x plus c, and there's the answer. Awesome, right? So this is the other way in which you can solve the same problem, depending which substitution you want to use. But sometimes that choice is only one correct and the one wrong. And how do you know when you made the wrong choice?
If you find it.
You make it worse, right? You make the problem worse. You can't fit all of the pieces in your substitution.
But why do they get different answers though?
Same answer. 1 over 6 secant to the 6, 1 over 6 tangent to the 6.
But wait, but it'll be tangent.
Look, tangent is the same as secant.
Gotcha.
And the extra plus 1s, they get absorbed in plus c.
Gotcha.
So those plus 1s, we don't worry about those.
Okay.
Because that plus c can be any value. 2 or 100 or whatever we need that to be. The lecture is over. I'm just going to put another problem. So for secant tangent, I still have we'll do another cosecant cotangent, which has exactly the same thing, except minus signs are all over the place. The pairing and everything is done the same for cosecant. You either save secant, cosecant squared or cosecant cotangent, right? Let's do another one of these first. I will argue that this one is too obvious, but then integral of secant squared x tangent to the 1/2. They could have disguised this better within a square root, but eh. So obviously, what are we to do here? U is equal to tangent, very good. And then du is the secant squared. So they try to trick you just by writing the secant squared in front of the tangent. They could have put a square root over the tangent instead of a half, and then make it like look worse. But this is literally one-step problem that you are supposed to know and be able to solve in Calculus 1, section 5.5, when you are learning basic U sub. Because this integral is just integral of square root of U, du. That's how cheap this problem is. It looks bad, but. So we are going to pick U equals tangent.
I saw like a low-key message from you. I didn't see a message. I was like, probably right. I didn't see a time.
I don't know, though, like, and then we got the uncorrect player, and a PhD in the same
Like
place.
the first time.
It's terrible. All seven grades.
I'm probably.
Oh, you deranked now?
I'm probably.
No, that's not your break.
I've never played Counter-Strike. I'm not seeing that.
Yeah.
I haven't had time, Professor.
Their world's full of
I haven't had time.
you make the time.
I'm a businessman.
Yeah, you make the time.
I can't.
What are you doing? Nothing. I know nothing. Yes.
We can continue. So real quick, u equals tangent x, du equals secant squared x dx, which makes this into square root of u du, which is u to the 3/2 divided by the 3, and you put a half up there, plus c. So the final answer is 2/3 tangent to the 3/2 x plus c, and the problem is solved. So this was problem 37 in your textbook. For integrals of cosecant cotangent pairs, we'll say same as secant tangent. You just have to watch for those minuses. Watch your minus signs. That's taken out here. I'll scream it out. So that's the only thing that you have to worry about. And what I'm going to do, just to illustrate this, I'm going to just take this problem 37 and rename it into the cosecant cotangent pair, because everything is identical. I have cosecant squared x cotangent 1/2 x dx. So this is identical problem as the one before, except now you have cosecant cotangent. Well, it's the same deal. The function u is defined as the cotangent x, which means that du is now negative cosecant squared x dx. We have to fix this negative sign, so we install two negatives, one in front of the integral and one for the cosecant. And now we just have negative integral of square root of u du, which is negative u to the 3/2 divided by 3/2 plus c, and in the next step you have negative 2/3 cotangent to the 3/2 x plus c. So as you can see, the problem is identical to the secant tangent. So everything that you learn and practice for secant tangent will immediately work for cosecant cotangent, except there will be these minus signs floating around because both derivatives and integral of these pairs have minus signs. And now we are done with 7.3. We're going to take a short break, and then we're going to do integration, trigonometric substitution. Integration by trigonometric substitution. So I will restart the stream for the new title.